The implementation of the Stack Abstract Data Type, ADT, using a linked list is one of the most flexible and efficient ways to realize the last in, first out, LIFO structure, because it allows dynamic memory allocation and avoids the fixed size limitation of array-based stacks. In a linked list-based stack, each element is stored in a node that contains two fields: the data field, which holds the actual value, and the next pointer, which links the node to the one below it in the stack. The stack is managed using a single pointer known as top, which always points to the most recently inserted node, ensuring that push and pop operations involve only manipulating this pointer. When the stack is empty, the top pointer is set to null, representing an absence of nodes. Implementing a stack using a linked list requires defining the node structure, initializing the top pointer, and providing functions for push, pop, peek, and checking whether the stack is empty. One of the major advantages of this implementation is that the stack grows and shrinks dynamically according to the program's needs, eliminating the problem of overflow that occurs in array implementations where stack size is predetermined only under exceptional circumstances, such as when system memory is exhausted. Would a linked list-based stack face overflow? To perform the push operation in a linked list-based stack, a new node is first created using dynamic memory allocation functions such as malloc in C. The new node's data field is assigned the value being inserted, and its next pointer is updated to point to the current top node. After that, the top pointer is updated to reference this new node, effectively making it the new top of the stack. This insertion at the beginning of the linked list guarantees constant time complexity O(1), regardless of the number of elements already present. The pop operation removes the node at the top of the stack. Before removal, an underflow check is performed to ensure that the stack is not empty. If top is null, then the pop operation cannot proceed because there are no elements to remove. If the stack contains at least one node, a temporary pointer is assigned to the current top node. The top pointer is moved to the next node in the sequence, and the memory occupied by the removed node is freed. The returned value corresponds to the data stored in the removed node. Pop is also an O(1) operation because it requires only pointer manipulation, making it extremely efficient for applications requiring frequent insertions and deletions. The peek or top operation retrieves the value at the top of the stack without removing it. This is done simply by checking whether top is null. If not, the data stored in the node pointed to by top is returned. This operation also runs in constant time and is used extensively in algorithms where temporary inspection of the most recent element is necessary, such as infix to postfix conversion, syntax validation, or balancing parentheses. Another important operation is isEmpty, which checks whether the stack contains any nodes. This is done by comparing the top pointer with null. If it equals null, the stack is empty, otherwise it contains elements. Memory efficiency is a major strength of linked list-based stacks because memory allocation happens only when needed, and no large contiguous blocks of memory are required. Each node exists independently, and nodes can be anywhere in memory, connected via pointers. This flexibility makes linked list stacks particularly useful in embedded systems, memory-limited environments, and applications where stack size can change dramatically during execution. Linked list-based stacks also integrate naturally with recursion. When functions are called recursively, the system uses a call stack internally, which behaves very similarly to a linked list stack. That is one reason why recursive algorithms often translate smoothly into user-defined stack operations. Another advantage of using linked lists for stack implementation is that insertion and deletion do not require shifting elements, unlike arrays where resizing requires copying or rebuilding storage. This significantly improves performance in applications where stack operations occur frequently and unpredictably. Despite these advantages, linked list-based stacks also have certain limitations. Each node requires extra memory for the pointer field, which adds overhead in comparison to array-based stacks that store only the data values. Additionally, linked list stacks may have slightly slower access time due to pointer dereferencing, although this difference is minimal in most practical scenarios. Furthermore, link structures can increase memory fragmentation if frequently used, because nodes may be allocated in scattered locations throughout memory. However, these limitations are generally minor when compared to the flexibility and scalability offered by linked list-based implementations. In terms of applications, linked list-based stacks are ideal for problems involving dynamic datasets, where the number of elements may expand and contract at runtime. They are used in expression evaluation, backtracking algorithms, compiler parsing, and memory management. For example, in-depth first search of graphs or solving puzzles like mazes or the towers of Hanoi. Stacks are used to store states, and the dynamic nature of linked lists allows unlimited growth as the search space expands. Similarly, linked list stacks are useful in computing factorials, Fibonacci numbers, and tree traversals using non-recursive methods. Overall, the implementation of stack ADT using linked lists provides a robust, scalable, and efficient structure suitable for a wide variety of computational tasks. It supports constant time push and pop operations, eliminates the need for fixed-size storage, and integrates well with algorithms requiring flexible memory usage. Its pointer-based design ensures that the stack grows naturally according to the demands of the application, making it a preferred choice for advanced programming scenarios, complex data processing, and real-time systems.